It's question show time. Your questions, my answers. As always, wherever you are, across my channel, question pops in your brain, just write it down. I'll gather them up and I will answer them here. Before I get into the question show, I want to remind you that I do a really cool weekly email newsletter. It's like a magazine. It's got like 20 plus stories. I write all the words in it. There's no ads. It's just a way for you to see all of the space news that I'm looking at for the entire week. There's probably like 40 or 50 links to various space stories throughout the entire thing. So if you want to check that out, go to universetoday.com/newsletter. All right, let's get into the episode. Vlad Shumakovic. Like ants attempting to explain human biology from a few encounters with hikers in a dense forest, humans continue to try to understand something they cannot observe. Even if our capabilities for observation were at their zenith, what we could observe would still not yet tell the full story. The more knowledge that is amassed, the more mental gymnastics are required to attempt to explain it. The more terminology is needed to describe it until it becomes its own foreign language, a language spoken by a small community who can describe it to one another in profoundly vivid detail just how little they actually know. Anything to avoid the dull reality of trying to survive here on planet Earth, I suppose. Yeah, and you're describing scientific progress. I mean, think of the irony here is that you are communicating to me, you're sending a message on YouTube with your computer that's connected to the internet. A computer, internet, the basic science that went into that, lasers, computers, silicon conductors, transistors, understanding quantum mechanics at the fundamental level to understand how signals can be passed, light through fiber optic cables, radio transmissions. Each one of these is basic science in that people went to try to understand the basic nature of reality itself. And nature does not give up its secrets very easily. Sometimes it's relatively straightforward. Other times it's a brutal, painstaking process that takes decades, maybe even centuries. And you don't know which one of those journeys you're on, the easy one or the hard one, until you just continue moving through this territory, discovery by discovery, building up this knowledge. And just because scientists use very specific terminology to explain their observations, just means that you haven't taken the time to understand them. My guess is that if you followed the journey, followed the discoveries one by one, and understood the architecture of where current understanding in cosmology is, you would appreciate the depth and the work that's gone into this by thousands of people over hundreds of years. But you know, this is YouTube and you just casually dismiss it. Here's the thing, you know, as you're commenting, maybe you're even using a smartphone, right? A wonder of modern technology built up by mountains of basic science. It's crazy. So if you don't appreciate the scientific discovery that's been made so far, my guess is you don't understand it. And generally, when we're trying to comment and critique on something that we don't understand, the first thing to do is to deeply understand it. And if you're not willing to take the time to understand it, then you're being lazy. But if you are willing to take the time to understand it, and you do get yourself to the point that you do have this deep understanding of all the works being done, then you're in a position that you can effectively criticize the work that's being done. And who knows, you might be able to contribute meaningfully to our scientific understanding of the universe. Just because we don't understand it yet doesn't mean that we won't ever discover it. And I like to describe this as an analogy of like watching a sports game. Now, I don't watch sports games, sports ball, but we're in the middle of the game. We're watching. We don't know what the outcome is going to be. We don't know who's going to win. But just watching the game can be really exciting. As the new discoveries are made, as the new observations are made, we get to see these step by step. And when we finally have an understanding of what happens, the more you understand about it, the more you're going to appreciate the outcome. So take the time to understand exactly what's going on here, and I'll bet you'll appreciate it with a lot more depth and clarity. Or don't, but just understand that you don't don't really know what you're talking about. I-1692. What would happen if they were able to use two of these methods of measuring the Hubble constant in the same galaxy? For example, what if a Type 1a supernova explodes in a galaxy and we also use the Maser distance technique around its supermassive black hole? Has this ever happened? I'm not sure if specifically Type 1a supernovae and masers have been calculated separately, but you can definitely use the redshift movement of the galaxy moving away from you and compare that against the supernovas or the masers or other methods of determining distance in the universe. And in fact, this is how astronomers double check or really calibrate their various measuring sticks for the expansion rate of the universe. You want to be able to check one object with 2, 3, 4 different methods of measuring the distance, and you want those to line up to know that your various measurement tools are accurate. And we do this, I'll give you a sort of a more classic example of this. So here in the Milky Way, nearby stars, we can measure the distance to stars very accurately using this technique called astrometry. And essentially, the classic example, hold your arm out at arm's length, go one eye back and forth, watching your thumb, and you'll see how your thumb appears to shift back and forth compared to the background. And astronomers do that, but you wait for the Earth to be on one side of the sun, and then you wait for the Earth to be on the other side of the sun, and you measure the angles to a star against the background, and you're actually able to watch the star blink back and forth for close stars. And you can use trigonometry to get at the distance precisely. Now, astronomers can do that pretty far in the Milky Way, and then there's another class of objects called Cepheid variables, which brighten and darken in a very specific way compared to their intrinsic brightness. And if you know their intrinsic brightness, then you can know how far away these things are, and they overlap. So you can use the astrometry method to measure the distance to a Cepheid variable, and then you can use the Cepheid variable method to measure the brightness to other Cepheid variables, and the numbers match. And then you can use that method to measure, say, the distance to, you can spot Cepheid variables in other galaxies and use that method to then confirm other methods. And so any method, any measurement technique that astronomers have developed, they have attempted to make them all overlap into different regimes of distance. Some work really well in close distances, others work really well in medium distances, and others work really well in far distances. But the goal is always to make them overlap so that you can double check always the tools that you're using to measure distance in the universe. Rod Novak. I've been listening to the Trojan Asteroids Astronomy Cast episode, and I wondered, could the Jupiter clouds actually agglomerate to something bigger, like the size of the moon, or is the chaotic gravity there too much for something like this to happen? It's really important first to just understand what it means to be orbiting around in a Trojan point, really the L4, L5 Lagrange points. And really, it's sort of a fundamental question about what gravity is itself. When we imagine gravity, we imagine these Trojan points, these L4 points. We imagine this hill that all of these objects are rolling downhill into, and they're spiraling around until they collect down into the very bottom of the gravity well. But that's not what it is. All of these objects are orbiting around this L4, L5 region, but it's not like it's a point. It's a region. And they are trapped within this gravity well, but they're just going to go around and around in whatever orbit they happen to have. And there's no reason why they would slow down their orbit, lower down into the gravity well any deeper, unless they collide with each other and things like that. So things will just keep orbiting around however they got into the Lagrange point, into the Trojan region. And just like in general, think about the sun. Imagine the sun is just another gravity well, and all of the planets and all of the asteroids and all the Kuiper Belt, everything just orbits around. It's not like the sun is this vacuum cleaner that's pulling stuff into it. In order for things to fall in and actually start to accrete, you need them to be colliding with each other and causing friction to each other. And that's the kind of thing you see, say, with a black hole. All of this material is orbiting around the black hole, but it's all bumping into each other and bouncing and slowing its orbits and pushing it closer and closer to the black hole. If you just had a single star orbiting around a black hole, it would just do that forever. There's no reason why it's going to fall into the black hole. It's only when you get this interaction with all these objects. So over long periods of time, you can imagine the Trojan asteroids bumping into each other, colliding, smashing, pieces coming apart, moving closer and down into the gravity well, but not in a significant amount of time. So even if you did take all of the material in the Trojan asteroid, it would be a fairly small object. I don't know the total mass of the asteroid, of the Trojan belt. I know it's similar to the asteroid belt, and if you took all the mass in the asteroid belt, it would only account for about 5% the mass of the moon. So even if you gathered it all up, there's not a lot there. Vidit. Thanks for this. Please split more of these videos into individual segments so that we can watch the parts that we are most interested in. Watching the entire hour-long video is not possible many times. I had suggested this in one of the previous videos too, but I'm not sure if you had seen my comment. We've had this recommendation before. I think people know that we produce a ton of content. There's the open space interviews that I do with really fascinating topics. There's the weekly space hangout. There's astronomy cast. There's the virtual star parties. Like, we produce a ton of content, plus the question shows. And then there's the guide to space shows, which are fairly short, very highly produced. And the thing is that to do all the other stuff, like for me to do an interview with somebody takes an hour of my time from beginning to end, 1 hour, and then the show is on the internet and you can watch it. And obviously there's no graphics, but you can listen to it as a podcast or you can just watch the conversation happen. When we make one of the Guide to Space, like of all of the stuff that we do, the Guide to Space episodes are by far, like by an order of magnitude, more complicated, more expensive, more time consuming for us to make. And so we have to use our time very carefully. Let's say it's going to take us 20 hours to turn a 1 hour conversation interview into something that's higher production value. What do we spend that time on? We have very limited budget. There's just my time, Chad's time. That's all we got. So I think that, you know, the conversation that we have, the weekly space hangout that we did about the cosmological crisis was so interesting that I thought, okay, let's turn that into an episode. And occasionally I'm sure there's stuff that's come along that would make sense as an episode. But if we do that, then we're going to have to take time away from some of the other stuff that we may do. Like we're doing an episode about a star that just disappeared. And that, again, that's the highly produced, a lot more complicated, a lot more time intensive. So it's always just a balancing act. And I mean, if you don't have time, you don't have time. I get that. If you do have time, then you do have time. And sometimes you just gotta trust me. You've just gotta trust that I'm gonna pick topics, that I'm going to pick guests. They're going to be really interesting, and you don't know whether or not you're going to enjoy it until you just start. And then you're like, whoa, this is really great. I really enjoyed this. And if we have more time, more budget, more patrons, we will do what we can, but we're just working with what we got. Brendan. Hey, not sure if you've answered this before, but if a star goes supernova, will that cause an adjacent star to go supernova as well? Could this cause a chain reaction with stars in the surrounding area as well? Keep up the amazing work, and thank you for all that you do. I'm sure you're imagining you've got like a bunch of stars, big star, goes supernova, hits a star nearby, that star goes supernova, like a chain reaction, like gunpowder or something. But it doesn't work that way. A star goes supernova when it has been fusing up all of this material in its core and it runs out of usable elements and it starts to fuse iron, and there's no energy from iron, and so the outer layers collapse inward and you get a supernova and a black hole. But supernova do cause other supernova in a more roundabout way. And the way they do that is that when you get a star forming in the first place, usually there needs to be some kind of kick that will cause a large mass of hydrogen to collapse down and start the star forming process. And so what will happen is, like, a supernova will go off. It will cause a shock wave that'll move through a cloud of hydrogen and helium and cause enough instability that will begin this process of the star starting to collapse and form. And if there's enough material in there for it to turn into a supernova, then in a few million years, you're going to get a supernova from that star as well. And then maybe that one will cause other molecular clouds to collapse, and so on and so forth. MC's creations. Really interesting, but I was thinking, let's say we create the technology today to begin to travel through the Milky Way. I can understand colonizing maybe 2 other planets around 2 different stars, but why would we colonize more than that? I can understand travel everywhere to know and study other places, but I can't really see an advantage to colonize the whole Milky Way. I agree that it's really important to distinguish between colonizing, settling other places in the Milky Way and studying and analyzing them. And those are two different things. And I think for the analyzing case, I think it's pretty clear. You send a robot factory to another star system, that builds more robot factories, they go to other star systems, and it slowly, by the speed of light, we get information about the composition of every single planet, every single star system, every alien species in the entire Milky Way. And that would be incredibly useful. We would want to learn that knowledge. Let's say we learned that knowledge and we found some worlds that were perfectly habitable for Earth life. Maybe we would want to settle it, but the distances involved are incredibly far. They could be hundreds of light years, thousands of light years away. And so does it really make sense? What are the ethics involved of having people be on a spaceship for multiple generations just so they can go live on a planet that's maybe as good as Earth? Do we need that kind of space? Does it make more sense for us to be able to build additional space here in the solar system where it's easy and quick to get to? So I agree that it doesn't really make sense in the near term for us to really think about ways that we would want to be able to settle other star systems until it's easy and convenient. And we're looking at hundreds of years from now, maybe even thousands of years, till we get to a point where we have control over enough energy that in a reasonable amount of time, we can send a spacecraft to another star system and set up shop there. But we're going to require some fundamental discoveries in physics, in various technology, or it's just going to take the accumulation over hundreds, thousands of years for us to get good enough that we could actually attempt something like that. So I think in the short term, it makes no sense to try to live anywhere else but here on Earth. And then eventually when it becomes easy to live in other places in the solar system, we should do that. When it becomes easy to live in other places in the Milky Way, we should do that. But until then, don't bother. Brian Stinsky, you were talking about a black hole being kicked out of orbit into a random trajectory. What would happen if it came close to the Earth? Say the distance the moon is from the Earth. That sounds kind of scary. Let's simulate that and see what happens. That's not good. All right, so let's simulate and see what happens if a black hole moves close to the sun. Also not good. The reason, of course, is because a black hole is going to have 8, 10, 20 times the mass of the sun, and that is going to completely disrupt the orbits of all the objects in the solar system, tear apart the Earth, the moon, the sun. Nothing can really compare against that kind of strength. Fortunately, we can see that this has never happened in the Milky Way. All of the planets are orbiting in roughly, nice ellipses around the sun. Clearly, a black hole has not moved through the solar system in the 4.5 billion years that we've been around, and so it's fairly unlikely that it's going to happen anytime soon. But if it did, it would be super bad. Mark Hathaway, is there one particular escape speed for a black hole to leave a galaxy? There is an escape velocity for the entire Milky Way, just in general, and that number is 550 kilometers per second. And just for comparison, the escape velocity from the solar system is about 42 kilometers per second. So it's more than 10 times faster. And it's not just black holes that can get, thrown out of the Milky Way. Just stars can do it. If you have some kind of interaction with the supermassive black hole at the heart of the Milky Way, or if you're in a binary companion and one star explodes, the other one is thrown out like a slingshot. As long as you're going faster than 550 kilometers per second, you are leaving the Milky Way and you're never coming back. Arturo Ramirez. Wait, if something moves faster than light, is it even possible to detect it? It depends on how it is moving faster than the speed of light. So right now, there is no way that we know of that you can move faster than the speed of light through the universe. You can only approach the speed of light and you can't go any faster. In fact, if you punch in the numbers for going faster than the speed of light into relativity calculations, then you go backwards in time. And so if you're going faster than the speed of light, you will be arriving at your destination before you left, which is pretty weird, but that's how the universe works. So let's imagine you're not moving through the universe, you've got some warp drive that you are warping space. Then our understanding of the Alcubierre drive is that it's instantaneous. So you turn on the Alcubierre drive and you distort space-time, and then you arrive at your destination. So you would see a spacecraft in one location, and then you would see it at its destination, and there would be no intervening movement that happened. But even if something is moving, or let me give you another example of a thing that is moving potentially faster than the speed of light, and that's galaxies that are really far away from us right now. That space itself is expanding and carrying these galaxies away from us potentially faster than the speed of light, and yet we'll still be able to see them. And I'll give you an analogy here. There are aircraft that can move faster than the speed of sound, but we can hear them. It's just that we don't hear them where they are, we hear them where they were. And so if there was some way to have a spacecraft moving faster than the speed of light in front of you, you wouldn't see where it is, you would see where it was whenever it emitted that signal, because the second it emits that light, then that light is going to be moving at the speed of light to get to us. So you would always be looking behind where the spacecraft was, but there's no reason to think why it wouldn't still be emitting light that we would be able to detect. Hope that helps. Rust in peace. Could we detect distant pulsars, then see how the timings alter as they recede from us? Would that work? Pulsars are one of the most useful tools in the universe for determining things like distance and time and speed and things like that, because pulsars turn sometimes hundreds of times a minute and with a very, very regular pulse rate. And so, of course, these are neutron stars that are rapidly spinning. They're blasting out radio waves that we're able to detect. And so if a pulsar is moving, say, in a binary system, pulsars moving towards us and away from us, and that changes the redshift of the radio waves as they arrive to us, which is kind of amazing. But the thing is that you would be able to detect essentially how quickly the pulsar is moving away from us, but you need to know its intrinsic brightness. And pulsars don't necessarily have a specific intrinsic brightness. They can be brighter or dimmer, and so you can't then know, oh, if I see a pulsar and it's this bright, then I know how far away it is and I can detect its movement, so that's really useful. That said, pulsars can be seen really far away. Pulsars have been seen, the farthest pulsar I think was like 50 million light years away in another galaxy, which is kind of amazing. And so you can do some really interesting things, but you may need to use some other technique to determine the distance to the galaxy, say using the Cepheid variable technique, and then you know that the pulsar is in that galaxy that's 50 million light years away, and then you can do other really interesting things with that pulsar, with the light that's coming from that pulsar. So pulsars are incredibly useful for all kinds of things, but to determine the distance to things, they need to be standard candles. You need to know how bright they are intrinsically, and then you see how bright they are visually, and then that tells you how far away they are. And pulsars aren't that useful for that process. Branch. How do we define the size of planets or minor planets with an atmosphere? Saturn is mostly atmosphere. Earth has quite a bit of atmosphere, and we heard that Pluto has an atmosphere which sometimes freezes down to the surface. Does Pluto reduce in size when the atmosphere snows down? Here on Earth, it's pretty obvious where the atmosphere is. You've got the ground, and then you've got the air, and that's the atmosphere. Pluto, it's very similar. You've got the icy surface of Pluto, and then you've got this really thin, tenuous atmosphere around it. It's obvious where the difference is. But what do you do when you have a place like Saturn or Jupiter, they're made of atmosphere? And so actually there's no distinct boundary where the atmosphere ends and the planet begins, because essentially as you go down deeper and deeper into the planet, it just gets more and more dense until it acts more like a liquid. And so say on Jupiter, that's about 1,000 kilometers. So at the very top of Jupiter, it's very wispy, atmospheric, but then as you go down, it just gets more and more dense and more hot. And then that material is acting like a liquid. And then if you go further down, then that material is acting more like a solid. But there's no real specific definition of where the atmosphere begins and ends. It's more a spectrum. Katsu Zatiochi. Hey Fraser, question, could we store colossal amounts of photons and use them as fuel in rockets? Perhaps collect them from the sun and store them in some kind of mirror arrangement. And when the rocket launch, we remove one mirror, releasing all the photons, lifting the rocket. So the problem you're going to get in trying to store photons is that they are going to heat up. They're going to be absorbed by your mirrors, and they're going to heat up the mirrors, and eventually the mirrors are going to melt, and then whatever's housing the mirrors is going to melt, because the more of these are just bouncing around inside, it's going to get hotter and hotter and hotter. Now, imagine that you could have a perfect mirror that didn't release any heat, which is impossible, theoretically impossible. Well, then you would be storing energy in this tiny, dense area. And if you got to a certain point, the energy would be so dense, you would essentially be creating a black hole. It's an idea of a Kugelblitz, but it's a black, store energy in a tight enough area. Just like if you store mass in a tight enough area, matter, you're going to get a black hole. And so we need some kind of intermediary step. And this is what batteries are. And this is this whole idea of energy density, that gasoline and rocket fuel and batteries, they all have an energy density, which you can take energy from the sun and you can store it in a compact area that you can then utilize at some later point, and you don't light the whole thing on fire and create a black hole. So antimatter is probably the best thing, as long as you can keep it away from the walls of your system. So you can turn sunlight into antimatter, and then you store the antimatter in some way, and then when you're ready, you can then turn that antimatter into pure energy by mixing with regular matter. And that's probably the most efficient energy storage system that we can think of right now. All right, here ends the question show. Sorry about the kids yelling. There's a daycare just got set up right by my house. It's random when they're out freaking out. As always, wherever you are, across my channel, question pops in your brain, write it down, I'll gather them up, and I'll answer them here, and I'll see you next week.